Have you ever wondered why water pressure decreases as water flows through a pipe? Even when there are no leaks, some energy is lost during the flow process. This loss of energy happens because of friction between the water and the inner surface of the pipe, which known as head loss due to friction. Assalamualaikum warahmatullahi wabarakatuh and good morning I bid to all. My name is Muhammad Nabil and today I would like to present my group's project entitled Head Loss Due to Friction. This project focuses on how friction between a flowing fluid in the inner surface of a pipe causes a loss of energy, known as head loss. We will discuss the theory behind head loss, the factors that affect it, the experimental procedure, and the results obtained from our study. Without wasting any time, let us begin our presentation. So, the objective of this project is to investigate the relationship between flow rate and head loss due to friction in a pipe system, to determine the friction factor under different flow conditions, to verify the applicability of the Darcy-Weisbach equation for calculating head loss, and last but not least, to analyze the factors affecting frictional loss in hydraulic pipelines. Next, we move to learning outcomes. At the end of this project, students should be able to explain the concept of head loss due to friction in pipe flow, calculate frictional head loss using hydraulic equations, analyze the effect of flow rate on pressure and energy loss, interpret experimental data and compare it with theoretical calculation, and last but not least, apply hydraulic principle in the design and evaluation of piping systems.
Hi, let's go see a problem statement. Water flow to a pipe is a rub against the inside surface of the pipe. This creates friction, which causes the water to lose some of its energy. This energy loss is called head loss due to friction. If the head loss too high, the water pressure becomes lower. The more energy is needed to pump the water and the whole pipeline system becomes less efficient. That is why this experiment is important to help us understand how friction affects water flow so engineers can design better and more efficient pipeline system. Hi, let's go straight to the basic concept. The main concept in this experiment is head loss due to friction, which means the loss of energy as water flow through a pipe. To calculate the head loss, we use the Darcy-Weisbach equation. This equation shows that when the flow velocity increases, the head loss also increases. We also use the Reynolds number to identify the type of the flow. If the flow is laminar, the friction is lower. If the flow is turbulent, the friction is highest, so more energy is lost. This concept is very important in real life, especially in water supply system, irrigation system, and industrial pipelines, where engineers need to reduce energy loss and improve system efficiency.
Okay, now we continue with the apparatus. The first one is rotameter. The second one is voluntary measuring cylinder. And the third one is flow control valve. The fourth one is global valve. And number 5 is experimental test pipe sample. 6 is apparatus frame. 7 we have the flow meter. And next one we have the Dyson PFA 10 head loss and pipe friction apparatus. And the last one we have the digital pressure gauge. Next we move on. Okay, now let's go to head loss experiment.
First step,
On the button. Second, open the control flow. Okay, third, insert the manometer fill pin. Okay, now select the first lead valve to open. Okay, then we wait until the flow water reach stable condition, which is
digital gauge.
Once it's done, repeat the same procedure for sudden contraction and sudden enlargement.
Here are the results. This table summarizes the experimental results for all 5 pipe samples. The Reynolds number ranged from approximately 6,400 to 36,147, indicating that all the flow conditions were turbulent. For the 4 smooth pipes, the absolute roughness remained constant at 0.0015 millimeters, while the friction factors ranged from 0.0060 to 0.00725. As the pipe diameter increased, the relative roughness generally decreased. For pipe 5, which is the roughened pipe, the calculated absolute roughness was 0.5584 millimeters, with a relative roughness of 0.03405. It also recorded the highest friction factor of 0.062, indicating that the roughened surface created greater resistance to fluid flow. These results were then used for further analysis of the relationship between pipe roughness and head loss. For pipe 5, which is the roughened pipe, the absolute roughness was not provided and therefore had to be determined from the experimental data. First, the pressure readings were recorded as 19.5 kilopascals at 0.1 and 17.1 kilopascals at 0.2, giving a pressure difference of 2.4 kilopascals. Next, the pressure difference was converted into a head loss of 0.25 meters. Using the Darcy-Weisbach equation, the friction factor was calculated as 0.062. The relative roughness was then determined using the Colebrook equation, resulting in a value of 0.03405. Finally, the absolute roughness was calculated by multiplying the relative roughness by the pipe diameter, giving an absolute roughness of 0.5584 millimeters. These calculated values were then included in the final results table for further analysis. Based on the experimental results, all 5 pipe samples were operating under turbulent flow conditions, with Reynolds number ranging from approximately 6,400 to 36,000. The smooth pipe recorded relatively low friction factors because their internal surfaces had very small roughness values. As the pipe diameter increased, the relative roughness decreased, resulting in lower resistance to fluid flow. For the roughened pipe, a pressure difference of 2.4 kilopascals was measured. This produced a head loss of 0.25 meters, a friction factor of 0.062, and an absolute roughness of 0.5584 millimeters, which is significantly higher than the smooth pipe. This shows that increasing the surface roughness increases friction between the fluid and the pipe wall, leading to greater energy loss. Overall, the experiment confirms that both pipe diameter and surface roughness have a significant effect on head loss, which agrees with the Darcy-Weisbach equation and fluid flow theory.
Hello, Assalamualaikum. My name is Kamarun Najmi bin Shaman, student ID 20 25 34 2704. I will now explain the discussion. The experimental results demonstrate a clear relationship between pipe dimension, surface characteristic, and energy losses in fluid system. The first one being flow type. All 5 pipe samples operate within the turbulent flow region, as evidenced by Reynolds number ranging from 16,400 to 36,100. Next, influence of pipe diameter. As the pipe diameter increase, the relative roughness K over D decrease, which directly contribute to reduced flow resistance. Moving on, impact of surface roughness. The significant contrast between smooth pipe and the roughened pipe, which is pipe 5, highlights the impact of surface texture. Pipe 5 exhibit a markedly higher friction factor, which is F equal to 0.062, and an absolute roughness of K, which is 0.5584 millimeter compared to the other samples. Then, we have energy losses. The data confirms that the higher surface roughness and smaller diameters increase resistance to fluid flow, leading to higher head losses. This performance aligns with established fluid mechanics principles and the Darcy-Weisbach equation, which dictates that energy losses is a function of both friction and physical pipe dimension. I will now explain the conclusion. The experiment successfully verified theoretical impact of pipe diameter and absolute roughness on fluid flow behavior. By calculating the friction factors and the head losses across different pipe samples, we observed that first, direct correlation. There is a clear direct correlation between surface roughness and the resulting friction factor. Higher roughness values create a greater resistance to flow. Secondly, pipe dimension. Pipe diameter plays a critical role in determining relative roughness and overall head losses. Last, experimental validation. We calculate values for pipe 5 demonstrate that even in turbulent condition, specific surface characteristic can be accurately determined through pressure difference measurements and the application of the Darcy-Weisbach framework. This finding confirmed that maintaining pipe surface integrity and optimizing diameter are essential consideration for minimizing energy losses in industrial piping system. That's all from me. Thank you.